Okay, we're going to go on with PS25BBlake and go further into the chapter. I'm on the second section, which is about types of bonds in this video. And we are in week 2.5, so the flip chart is PS25.2021. This lab I'm not going to talk about right here. Hopefully we can do this in class. It's a lab over ionic bonds, covalent bonds, and hydrogen bonds. And for your reference, we will use ice for hydrogen bonds, and we will use sugar for covalent bonds, and we will use sodium chloride or table salt for ionic bonds. And we'll investigate with them to try to see what they do. In that next section on types of bonds, from page 558, we're going to talk about ions. If it gains a lot electrons or from over here, or loses electrons from the left of the periodic table, it is an ion. An ion is just a fancy word, or not so fancy word, for a charged particle. It's either more or fewer electrons than protons. So, if you have potassium and iodine's sitting here and it's got on its outside layer 1, 2, 3, 4, 5, 6, 7, and once one more, and potassium on its outside layer has 1. These are called valence electrons on the outside. This will try to get rid of that one, and the iodine will try to take it, and it'll be a very strong reaction. This is the one that's listed in figure 8 at the top of the page. Right here. This is the same thing. I have my electrons drawn as dashes, they've got them drawn as dots. It's okay. I've got some of them here drawn in as dots on some of these examples. What you end up with is, boom, that ion goes over here. You lose a layer here. This is now negative because it picked up an electron. It's called the iodide ion now. This is now positive because it lost that electron, and it's called the potassium ion now. And now that this is positive and this is negative and they're opposite, they're going to stick. And the product is called potassium iodide. I don't know why I have KCl there. It should be Ki. Okay, so let me change that. Potassium iodide. The positive and negative ions that result from the reaction attract each other and form a solid salt. Now there are many salts. You got sodium chloride is table salt, but potassium iodide is a salt. If you take something from the left, it's a metal that gives electrons. Something from the right, it's a non-metal that takes electrons. You will end up with a salt. You can even make salts out of something we call polyatomic ions that we'll discuss here later. Now, how do you do magnesium reacting with chlorine? This is a little trickier, because magnesium, with potassium and iodine, we had given one and taking one. That's not what we have this time. We have magnesium, which is in the give two column, which I think was with fluorine, which is in the take one column. How does that happen? Well, we have chloride. It's in the same family. Well, chloride wants one electron. If we put one there, what are we going to do with this other electron? Get another chlorine and put it there. And when you get that other chlorine and those two electrons move, you'll lose this layer because one electron went here, one electron went here. This is two positive, and this is chloride minus, and this is chloride minus, and we write MgCl2. One of these and two of those. That's how that's done. Now, that was ionic bonding. If we go to page 561, they're going to talk about covalent bonding, which is not a transfer, but a sharing. So I just showed you with magnesium chloride, the same diagram that they have down here, just looks a little different because I used hashes and they used dots. But notice it says molecules up here. Covalent bonding. That's what we're going to discuss now, the sharing. The attraction that forms between atoms when they share electrons is known as a covalent bond. The neutral particle that forms as a result is called a molecule. There can be multiple bonds like double bonds and triple bonds, which is what they talk about here. They've got oxygen with a double bond, nitrogen with a triple bond. Okay, it says see figure 11, page 561, and maybe I'll put that in the notes, but that's what I just showed you. Okay, oxygen kind of looks like this. Here's an oxygen that has 1, 2, 3, 4, 5, 6. There's an oxygen that has 1, 2, 3, 4, 5, 6. Well, they both want 8, so how are they going to manage that? Well, if they get up in each other's business, and this oxygen has its 1, 2, 3, 4, 5, 6, but it shares that electron and that electron. And this oxygen has 1, 2, 3, 4, 5, 6, but it shares that electron and that electron. Everybody has access to 8. And we draw this shared pair and this shared pair as 2 sets of dots. So it looks like this. How many electrons does each oxygen have access to? I am going to redo the dots here so they're a little clearer to see. Okay, how many do they each have access to? Well, this one now has access to 2, 4, 6, 8. And this one has, one on the right, has access to 2, 4, 6, 8. So as long as they stay together and share, everybody has the 8 they need. Nitrogen, it would triple bond. They have 5 and 5. If they overlap, and I don't know that I can really draw that very well, they can. This type of diagram really doesn't work well for this. You have to use a different type of a diagram. But they share. And how many do these each have access to? Well, if they put 3 sets between them, this one has access to 2, 4, 6, 8. And the one on the right has access to 2, 4, 6, 8. As long as they get together and they share them, everybody has access to the 8 they need in a triple bond. Okay, let me make sure I'm on time here. Okay, we're good. The sharing can be one of 2 ways. It can be equal or it can be unequal. If the sharing is pretty equal, because these two are the same, then you end up with something that's called nonpolar. It doesn't have a positive end and a negative end. All polar means is your molecule has a positive side and a negative side. That's all it means. If they share unequally, the result is a polar bond and the molecule has ends that are partly charged. For example, if I bond bromine with fluorine, fluorine hogs the electrons and pulls on them more strongly, and the electrons are hanging out down here, and bromine is left without as many. So we draw an arrow this way to show the electrons went to this side, and we leave a little plus here sign to show that this side is kind of positive. And we can even put this symbol in here. It's the Greek letter delta. It's our modern letter D. with a positive, and this means that the bromine is partly positive, and a delta negative means this side is partly negative. So we end up with a molecule that's got a partly positive side and a partly negative side, and these want to line up and stick to the next one. You know, another bromine, fluorine here that's positive, negative. Your opposites want to attract molecule to molecule. Okay, let's go over these. Section review. Page. You need to read that section. 564, number 8, compare and contrast ionic and covalent bonds. All right, I don't have anything written down, but that's okay, because I'm going to show you where it is. Because you go back here, okay, covalent is sharing. Well, let me go all the way back here. Let's do this. Aha, here we go. Right here. So you can pause it if you want. Here's your answer to number 8. Here's your answer to number 8. Ionic bonds happen when electrons are given by one atom and taken by a different atom. They occur between a metal and a non-metal to make a salt. Covalent bonds happen when electrons are shared between atoms. They occur between two non-metals. Molecules are made with covalent bonds. That's your number 8. Number 9. Determine the type of bonding in CaO and SO2. This one is a metal. Oxygen is a non-metal. So which one's that? So this one is metal with non-metal. So this one's going to give electrons, this is going to take electrons. And this one we have two things in the upper right hand corner. This is going to be between two non-metals. And they're going to share. So the top one is calcium oxide as ionic. The sulfur and oxygen compound is covalent. I don't remember if it was sulfur dioxide or sulfur trioxide. Sulfur dioxide. So this is ionic, this is covalent. If you have your sound on, you know that. Identify the following compounds as polar or non-polar covalent. Okay, HBr is going to be polar, Cl2 is going to be non-polar, H2 is going to be polar. Okay, here's how you know. If they're the same, they're going to be polar or non-polar because one isn't stronger than the other. But the farther you go, oh, here we go. The atoms that are closer to fluorine in the periodic table pull more on the electrons and you end up with polar bonds. So bromine is a couple positions below fluorine. It's going to pull on the electrons more strongly than hydrogen is. So the electrons are going to hang out down here. That's going to make this side negative and this side positive, and that's going to be polar. With water, water's up there close to fluorine. It's right next to it. Hydrogen's over here. The electrons are going to hang out down by the oxygen and make the oxygen side of the water molecule partly negative, and this side partly positive. It's going to give it two oppositely charged ends, and it's going to be polar. Water is very polar. So polar, non-polar, polar. Get your sound on, you got that down. From the given symbols, choose two elements that are likely to form an ionic bond. So you need a metal with a non-metal. That's your ionic bond. Okay, so here they are. Oxygen, neon, sulfur, calcium, and potassium. Okay, this one isn't going to bond at all. So ionic is going to be something from the left, like calcium or potassium, with something from the right, oxygen or sulfur. So we're going to form calcium oxide, calcium sulfide, or potassium oxide. Those are all going to be ionic. The ones that are going to be covalent, because they're non-metals and they're going to share, is sulfur and oxygen. What about calcium and potassium? Well, they'd make a metallic bond, and we're not asking about that because chemically it's not interesting here in this chapter. It just makes an alloy. Remember, neon doesn't bond. 13. Aluminum oxide can be produced during rocket launches. Show that the sum of the positive and negative charges in a unit of Al2O3 is 0. Aha, this is aluminum. This is oxygen. This wants to give 3 electrons away. This wants to take 2. 3, 2. I actually looked at this example after the test. At least for gold we did. Hopefully for green we did too. We got to move 6. 2 3s, 3 2s. So 2 3 4 5 6. I need 1 2 3 4 5 6. So on the next screen I probably have arrows. There we go. Once these two move here, and this one moves here, and this one moves here, and these two moves here, we have ions. That's probably the next one. Ta-da! And it becomes Al2O3 because I have 1 2 aluminum and I have 1 2 3 oxygen. These fingers count electrons. These numbers count atoms.